All right, everyone. I guess we're going to be able to start. So welcome, everyone, to the IEEE workshop on topological data analysis and visualization, TopoInVis. And it's a workshop that we organized with Tala bin Masood and Vijay Natarajan, who couldn't make the trip, Paul Rosen, sitting here in the front row, and myself. So this workshop is about computational methods using topological concepts for data analysis and data visualization. The goal of the workshop is to enable a fast dissemination of theory, algorithms, and applications of topological methods in data analysis and visualization, and also to work for community building. So TopoInVis, for those of you who haven't heard about before, it's pretty established workshop series. We had 8 editions in the past since 2005. It was taking place every 2 years in Sweden, Japan, and other countries. And previously had this sort of a retreat-style kind of workshop for 3 days. And recently, the steering committee of TopoInVis decided to remodel a little bit the organization of the workshop. So the way it happens is that there was a call for proposals, and people could make some proposal to suggest a change of organization. There were 2 submissions, and then there was a vote among the steering committee. And the decision was ultimately to have a sort of satellite event at IEEE. And this is the reason why we're having TopoInVis this year in Oklahoma City. And the ambition of the proposal that was selected was to try to increase the diversity in terms of communities and applications, to have more exchanges with other people interested in Viz, but also in other fields. For the technical papers, the selection process was working with a deadline in mid-June and notifications in late July. Each paper was reviewed by 3 IPC members, and the International Program Committee had 28 members from the Viz community, but also from applied math, from machine learning, and all. And we applied for a full-day workshop, and we got given a half-day workshop. So we're going to have a very entertaining format for the presentations. It's going to be very fast. It's going to be, you can view that as sort of very long fast forwards. The idea is to invite you to consider reading the paper. So the speakers will try to convince you to read their papers. The program is organized as follows. We'll have a keynote, 12 papers, and also early career research lightning talks. And we'll conclude the afternoon with the best paper award and closing session. For those of you who were not in the room this morning, I will advertise again the fact that we have an informal get-together dinner at the place called Fassler Hall. It's roughly 30 minutes walk from here, and you can take the trolley if you prefer, and starting at 6 p.m. So you're all welcome to join, of course. And now I'd like to thank everybody who contributed to the organization. This was a big teamwork. So we thank all the IEEE's global organization because they provided a lot of support. The keynote speaker, of course, the authors, the IPC member, the other committees, and I'd like to thank also my fellow workshop organizers, Vijay, Tala, and Paul. Everything went insanely smoothly. That was very efficient and smooth, so this was really nice to organize. All right, and without further ado, I will now introduce the keynote of the TopoInVis workshop, which will be given by Robert Greist, who is a professor of mathematics and engineering at UPenn. So Professor Greist is, and his staff made some significant contributions to the field of topological data analysis and algebraic topology, and he's also interested in the creation of educational content for mathematics. And without further ado, we'll now switch to the keynote. Thank you very much, Professor Greist.
This is going to take a minute. My apologies while we get this switched over. That should just take a minute, hopefully. There we go. Okay, great. Let me, first of all, start a timer and then say thank you to the organizers who invited me to come here and speak. They said, you can talk about whatever you want as long as it has to do with visualization. And I said, great, I never get to do that. So they don't know what's coming, right? Right. In the same way that you don't know what's coming, in the same way that I didn't know what was coming until a couple of days ago when I had time to work on this talk. So this title and the abstract I had no idea what I was going to do at the time. What this is going to wind up being is a very weird talk. Unfortunately, I'm not going to be talking about topological data analysis. I'm not going to be talking about persistent homology as much as I love those things. I would love to talk about them. This is going to be a much weirder talk, a little bit more practical later, but right now, a little bit more God's eye view. I want to take a big picture, share a couple of thoughts on visualization, visual imagination, visual media. Back in the day when I was trying to learn topology, I did not have the kinds of resources that you have today. I had books, and the way I liked to read the books was to look at the pictures and try to reconstruct what the incomprehensible text was saying based on what I saw in the pictures. And sometimes that didn't work so well. Sometimes it worked great. I remember Rolfson's book on knots and links being one of the things that really just got me into topology. Even though, from a technical point of view, the images themselves are, there's not much, right? They're hand-drawn, they're very simplistic, but they capture an essence of what is going on and made it really easy to understand. Maybe you learned topology from Alan Hatcher's wonderful book. I was a grad student at Cornell when he was writing this, and what we had was a very compressed, printed out copy on a dot matrix printer with no illustrations. So that is what I had. Things have gotten a little bit better over time. You look at an example of a really great, well-illustrated mathematics book like Needham's Complex Analysis. There are others as well that really take advantage of what the visual medium can do in the service of explaining things, in the service of helping clarify what's going on, even in fields that aren't so obviously visual. There's still an opportunity for a diagrammatic representation of mathematical entities that can really tap into the visual processing that is important to learning. Now, these are books. These are static illustrations. There's nothing fancy about this because these are early days. We are very much in the early days of the use of visual media to communicate. You go back in time to when comic books were a thing, and you look at the technical quality of the drawings. They're not what we're used to seeing today. There has been just a huge jump in what we're able to communicate as far as storytelling through visual media. The example that hits much closer to me, because I am a secret gamer, is video games. I had the old Pong system when it first came out. That's how old I really am. And I was geeking out with Pac-Man when I was a preteen. This was a big part of my life. And I have seen through strictly less than one lifetime, an incredible revolution in terms of what you're able to do. If you look at what the latest modern game engine can do, this is Unreal 5. It's incredible the degree of resolution you can get through real-time rendering and ray tracing. And that is not all. This is, what is this? This is a shot from a movie? Is this a video game? It's both and it's neither. This is from The Matrix Awakens, which got airdropped to anybody with a News Cycle Xbox or PlayStation 5 last November, December, sometime around there. And it's a giant Matrix megacity that you can just walk around. And it feels like you're walking around in a movie because they use the assets from the latest movie to build this. Not only can you walk around this enormous, and I mean enormous, city, you can boost a car, you can drive around. Of course, it being the Matrix, you can fly. You can fly around and see just how big this city is. You can fly up to a window, look in the window, and see what's hanging on the walls. It is absolutely incredible. Blew my mind away to a degree that nothing else had since open world games like Skyrim had come out. This is the thing that made me stop laughing at Facebook pivoting to Meta. The whole metaverse thing that I thought was overblown at first, I don't think so anymore. This is the thing that changed my mind. Of course, since last November, last December, there's been 1, 2, 3, 4, 5, half a dozen revolutions in AI-generated art. I got on the Midjourney beta back in, what was it, March, and thought that that was just an absolute sea change. And since then, we've had DALL-E 2, we've had Stable Diffusion getting open source released, and now that stuff is getting integrated everywhere, all over the place, in Adobe products. It is very difficult for me to keep up with what is happening in this world. We are very, very much in the midst of an exponential blow-up in terms of what we're able to do to produce visual content. This has manifested itself on the side of entertainment most strongly so far. I think it is very much worth our time and energy to think about how this can, should, will impact both the research and the educational endeavors that we are involved with. And that's what I want to talk about for the rest of this talk. I want to focus on what can you do to take advantage of the ability to generate lots and lots of high quality art. What can we do that's different from what is done in entertainment? And I want to keep this advice on the practical end. And so what I'm going to do is literally give some advice. I'm going to give 4 words of advice. It's advice, it's not a command, so you don't have to do this. And I'm going to toss it out. Some of it's going to be more or less conventional or controversial. And I'm going to try and leave some time at the end for some feedback, including pushback. That's fine. I'm going to start off with something that I think is uncontroversial. First word of advice is just produce. Just start making stuff. Do it on a schedule. Force yourself to produce visual content consistently and just get it out there. I'm not going to show you pictures of stuff that I was drawing 10 years ago because it was so utterly bad and embarrassing, but I will show you pictures of stuff that I was doing maybe 6 or 7 years ago when I started writing a book on applied algebraic topology. I set some rules for myself. I didn't know any fancy tools. I was just trying to learn Adobe Illustrator. But I just set some rules. I can't use color. I just have to use line drawings. I can use dots and arrows and shading, and that's it. I'm not allowed to use any labels, not allowed to mark anything, not allowed to actually describe what anything is. And the rule was I had to try to communicate all these different ideas in algebraic topology just using a visual language. This was the art training that I never had, in that it forced me to think about good design principles, to think, if these are indeed good design principles, to think about how to communicate without the crutch of being able to explain stuff. In the text itself, the figures are never called out. It never says, look at figure 23 and you'll see. No, that's not the way it works. These are the exercises for the text. If you understand what portion of the text a particular figure is talking about, if you can understand what the figure means, then you have solved the puzzle. You have understood what is going on in that. I would just set this up where every Saturday morning I would take the entire morning and draw some figures. Had to get so much done every week took a long time, but by the end of that, just producing content on a schedule, I found that that was so incredibly helpful. And so I recommend it to you as well. You can do a lot even without fancy tools. This stuff is a tiny bit fancy in the sense it was done with Adobe Illustrator, but you could have done 95% of this with PowerPoint, which is my favorite tool, or at least was my favorite tool until a few years ago. This slide is all in PowerPoint. It's 100% PowerPoint. This is 10 years old. I made this 10 years ago when I was producing calculus materials for my students, for some online initiatives that Penn was doing with Coursera. And it's fantastic what you can do just with PowerPoint and maybe a Wacom tablet attached so that you can draw some stuff and import it in. Again, nothing new here. It's just, wow, there's a lot that you could do with PowerPoint 10 years ago, and PowerPoint has gotten a lot better since then. This is now just absolutely standard. Anytime I'm teaching a course, I'm definitely using just a little bit of simple animations within PowerPoint in order to animate, illustrate what is going on. Again, if you don't want the burden of having to learn really, really high-end software, start off with something that you can work with easily, and PowerPoint is a great example of that. So, first word of advice is just produce. Just start making stuff, preferably on a schedule, preferably where you're under a lot of pressure to get stuff out every week. Second word of advice is also hopefully uncontroversial, and that is ascend. Don't just stick to using PowerPoint. Learn some more serious tools for being able to do stuff. Go from 2D or layered 2D in PowerPoint to full 3D. So what do I mean by that? Let me show you some images that start off looking two-dimensional. This is something that I made over the past, I don't know, month or so. This is a simple quasi-crystal tiling, and there's actually a bunch. And they're pleasant to look at, but they're inherently two-dimensional until you start varying things up a little bit. And then there are some elements that look a little bit more layered. All of these are not generated with 2D software, not generated with Illustrator or Photoshop. They are generated in a 3D modeling software and then just using slight modifications of the same exact rig to generate all this variation in terms of the visuals that you see. I'll talk more about the actual software in a couple of minutes, but let me just say that there's one thing that does all of these Penrose tilings. It's a simple L system that you can look up the code for that online. It might even be on the Wikipedia page. I can't remember where I ripped it off from, but you pop that in and then just start doing a little tiny bit of the stuff you do in three-dimensional software on top of it, cloning, laying down different spline widths, setting up geometry in that way. This is the same type of 3D software that I am currently using for a video series on topological data analysis to help teach that to people who are just starting to get into it. I'm thinking about this at an advanced undergraduate level. This is a project that I'm working on with Vidit Nanda from Oxford University. He has been writing up the lecture notes that go with this. I'm working on the video portion of it. I'm much slower than him. So the lecture notes are up on his page. The video is not quite yet. I have, however, been practicing by working up a couple of static illustrations for the chapter headings, just to capture ideas behind things like homotopy, homology, exact sequences, cohomology, persistence, things like that. And here you could see there's really some depth, some 3D stuff going on inside of these images. So cool, but the question that everyone keeps asking me is, what software do you use? I get really tired of that question on Twitter. Every time I post something and I get in the DMs, what software package do you use? In the past, I've been a little reluctant to talk about that for a couple of reasons. One is that there isn't one package, and it's difficult to use and to encourage other people to use, or at least it was until rather recently. I will tell you what I use. It is Cinema 4D, which is really kind of obvious to anybody who is in the graphics world. You can tell what's C4D, what's Maya, what's Houdini. It's pretty obvious once you've been working in the space for a little while. But everything I do nowadays is all C4D. The reason why I couldn't unambiguously recommend it in the past is that it's really expensive. This is not free. This is commercial software. You get all the benefits of commercial software in the sense that it's powerful, updated frequently, well taken care of, going to persist, but very expensive. Here's the cool part. When they got acquired by whoever bought them out, they now have an educator's license, which is ridiculously cheap. I have a commercial license, and that's ridiculously expensive, but they make for educators a commercial license. It is $10 for 6 months of use. You get a bunch of other stuff with it. I'm not shilling for them. I'm just really excited that I can now recommend this to my fellow educators and researchers without telling them, oh, you have to go out and spend $1,200 a year on this. I very highly recommend this software to you for a couple of different reasons. One of which being that it's not only good for 3D, for modeling geometry. It's called Cinema 4D because, of course, it does animation. And it does animation really well. And this has been the thing that has influenced my teaching almost more than anything else. The reason that I'm not going to be here for the rest of the conference is that I got to go teach tomorrow. I teach a lot. I'm teaching dynamical systems tomorrow morning at Penn to all of our engineering students. I'm in charge of all the multivariable calculus courses at Penn. I'll be teaching that tomorrow afternoon for trying to teach dynamical systems, how systems evolve in time. Having animation is absolutely important. Trying to draw pictures of a ball bouncing on a sinusoidal table is, you just cannot communicate how the dynamics is so naturally and obviously chaotic from a static animation. It's so much better to see it moving. A little bit later, towards the end of the course, I'm going to talk about models for chaotic dynamics, one of those being the Smale horseshoe map. This is the canonical example of a two-dimensional chaotic dynamical system. A homeomorphism of the plane where you stretch the square out, you fold it over, you lay it down on top of itself, and you iterate. You get this sort of taffy pulling effect. When you do that, it's a homeomorphism, so that means you could take the inverse map, you could take the square and run it through the inverse. And if you look at the invariant set in the square, the set of points that remain under all forwards and backwards iterates, I have to prove that it's a Cantor set. Kind of difficult to do if all I've got is a chalkboard to work with. But with video, with animation, it's so clear. It's so beautiful. This has been written about so many times in so many books, and you never really get at it the way that you can do so with a nice, smooth animation. Of course, dynamical systems is full of so many cool examples. Next to calculus, next to topology and applied topology, I think dynamical systems is one of the things that I just most love to teach from the point of view of being able to animate stuff and show students the dynamics, in this case, the dynamics of synchronization of a bunch of coupled oscillators. There's a number of different effects that you can pull into use. Of course, the classic example of a chaotic dynamical system is a double pendulum, and it's really cool that you can build these things and swing it around and see it. But when you're simulating it, there's a couple of things that you can do. You can run a tracer, so you can see the path that is cut out. You can have two of these layered directly on top of each other to see the sensitive dependence on initial conditions. All those things that you can do in simulation that you can't do with an expensive in-person rig, kind of cool. Now, what's interesting about that system, about this system, this being a forced duffing equation, again, a chaotic dynamical system, you have a mass between two slightly compressive springs, and you shake the rig back and forth. The horizontal position of the mass traces out some erratic, chaotic dynamics that's modeled by this simple forced second-order ODE. What's interesting about all these systems that I'm showing you, from the bouncing ball to this, is that I'm not simulating the dynamics in the sense of solving the differential equation using Runge-Kutta. I'm using the fact that the software has a physics engine built right into it. I'm saying, this is the mass of this pink ball. Here are the spring constants for these yellow springs. Shake it back and forth, and what happens? This is exactly what happens, and it's what is captured in a duffing equation. That's kind of cool. That's not the only kind of system that you can set up. I love this classic example of a mechanical linkage whose configuration space is a hyperbolic surface of genus, I think it's 3. It's either 2 or 3, depending on the lengths. But it's got a natural hyperbolic geometry to it. So when you spin this sucker, it gives you geodesic flow on that hyperbolic surface. That is an Anosov system. It's very chaotic. Robert Mackay built an example of this machine, and it's a super cool device, but it's expensive to make. You have to get these parts, you have to get the low friction bearings. So easy to simulate this thing in C4D or equivalent modern software that's got a physics engine built into it, and then you can see the chaotic dynamics really nicely, really cleanly. Of course, you can do the classics. You can take a differential equation and then draw the orbits to it. I think everybody does the orbits of the Lorentz equations at some point because it's super cool, but this is why I get a little annoyed when people say, what Python package are you using for this? Folks, you're not going to get this kind of stuff just with raw Python, because you've got to have the camera angles, you've got to get the geometry, you've got to get the materials right. I very much appreciate what more commercial industry-level software allows me to do easily, as far as taking a tiny bit of Python, solving the differential equations, and then actually rendering it out to be artistically interesting. When I'm teaching bifurcation theory, it's hard to come up with cool examples of bifurcations. On the left, you've got a supercritical pitchfork. On the right, you've got a transcritical. Many of the examples that you read about in textbooks are from systems that are hard to see. Population dynamics, dynamics of a laser, things like that. But one of the things that I had a lot of fun doing was actually just building a whole bunch of mechanisms that explain different dynamical features, different bifurcation features, just using a combination of spring forces, magnetic forces, mechanical forces, to then let the system run and then show where the stable and unstable equilibria are. My students have enjoyed that a lot. This is some fidget spinners that I made in silica and popped some repelling magnets into the holes on the ends, and then just give it a spin and let it go. And these things are all pushing against each other, and you get these dynamics that when you first look at it, you're like, oh, it's periodic. And then, oh, woo, it just moves, and oh, now it's in a different spot. This is great for illustrating what happens in Hamiltonian systems when you've got these islands of periodicity and then some little tiny chaotic meanderings between them. And what's so cool about being able to simulate stuff in a 3D engine is you can build things that you could not physically set up. I think I would have a hard time getting the fidget spinners and the magnets and getting this thing. How would I suspend it? What would I do? But being able to build it in silica and then see it operating in the same way is just super satisfying, super satisfying. I very much think that we should scrap undergraduate physics lab in mechanics class. Just build everything simulated in the metaverse so that you're running your experiments in silica. But that's a different story. Of course, gravitational forces are easy to model in these game engines. This is a simple system called a Sitnikov system, where you have two identical massive bodies orbiting each other on ellipses. You release a very tiny mass on the axis of symmetry between them, and that little tiny mass gets pulled at varying strengths. You can prove that it's a chaotic dynamical system, all kinds of interesting things you can prove about it, but it's super cool to just set it up, let it run, and then see that the results of that proof actually work out the way that it's supposed to. All of this stuff, again, you just bop it into the 3D software. I use Cinema 4D for it. It's got built-in simulation tools. I use this in my calculus classes as well. This has totally changed the way I teach calculus at Penn. It's totally changed the way that everybody at Penn is teaching calculus now. This week in multivariable calculus, we're doing Lagrange multipliers. Last week, we did level sets and gradients. And you'll see the call out to Morse's old video here. This ability to draw pictures of level sets to see how you're sweeping out different things is really helpful for the calculus students and gives me a little chance to advertise some topology secretly inside of calculus courses. Oh no, this is being filmed. Oh, cat's out of the bag. Okay, next week we're doing multivariate integrals. We're going to be doing Fubini's theorem, and it's going to be the same thing, trying to get them to see what's going on with double integrals, triple integrals, and then using that to motivate higher dimensional integrals as well. The ability to augment the in-class teaching that we do with a video text component has been really helpful. The students are liking it a lot. In about another month, we're going to be at that part of vector calculus where we're doing the things that really just frustrate the students to no end. Green's theorem, Gauss's theorem, Stokes' theorem. So hard to understand, so hard to grasp, so hard to visualize these things. On the one hand, it's kind of a good exercise to see who can make the cut, who can work with those equations and actually visualize what's going on. On the other hand, why filter out that many students? Why not give them a little bit of a boost in terms of understanding what is actually happening in Green's theorem? Why there are sort of two different versions of Green's theorem based on something like a curl and something like a divergence? The topic that we all want to talk about, the reason why we're here today, is the topological data analysis stuff. I wish I had a little more material to show you about that, but I am slowly trying to build up some tools for doing that really nicely. I recently wrote a rig for C4D for doing Viator's-Rips filtration, for building the 1 skeleton, the 2 skeleton, the 3 skeleton, et cetera. I've got some other rigs that I'm working on for importing point cloud data in terms of CSV files, in terms of JSON files, and then building stuff based off of that. Once you get that in there, then C4D's got all these native tools for being able to really illustrate, animate the stuff, get it to do whatever you want, and have it look super cool. And why not? Because having it look cool is a big component of getting students interested in a subject. This is one of the reasons why I'm so bullish on algebraic topology. We didn't used to draw pictures in that subject. And I think as a result, we lost a lot of people. One of the reasons why these tools are becoming so much more popular in applications is that people can see what's going on. This is something that I just did this past week, and I'm really happy with it, so I wanted to show it to you. This is just illustrating the simple lemma that any finite simplicial complex can be thought of as a subcomplex of a single high-dimensional simplex. Is that a surprise? No, it's not a surprise. It's not deep, but when you're approaching the subject for the first time, and you think, whoa, I never thought about that, that's really cool, to be able to see, on the one hand, a formal proof of it, and then on the other hand, an animation. Oh, wow, yeah, okay. Maybe that is kind of obvious. I think I get it now. One of the things that I like very much about C4D is that it's really easy to learn compared to something like Maya, compared to something like Houdini, things that are of equivalent power. C4D is, how should we put it, low class, right? Anyone who's a real graphics person works in Maya, works in Houdini. C4D is like for the, yeah. In part, this is an accident of history. This software was developed and most used by people in newsrooms. You know, the weather stuff, or the sports text that comes on the screen. Just really, that was their market for a while. Now it is used in things like TV shows, movies, stuff like that. But they had to make this really easy for people who work in the weather room to use it. And so it's very easy to learn. What's good for us, for people who are fine with the technical stuff, is that there are Python backdoors. I've written up some nice code for doing Viator's RIPS filtrations, for doing a whole bunch of other rigs. They are moving to a node system. They're rewriting the core engine to make it more Houdini-like and node-based, with some plans to allow people to write modules and then release them. That, I think, bodes very well for the future of being able to use this, build tools, and then share it with other people who might find it useful. Again, this is the software that I know that I like. This allows me to do stuff that is just so super cool. I was so hesitant for so long to take a leap into 3D. I tried playing with Adobe After Effects, I don't know, like 7 years ago, and it was a complete failure. I just couldn't get it. C4D, I found, even though it's much more powerful, I found it much more easy to use. I've sort of mentioned interstitially there are alternatives. Houdini is probably the thing that I would learn if I could go back in time and redo it all, just because it is so much more powerful than anything else that's out there that I have seen. It is harder to learn. It doesn't have quite the full-featured educational license that C4D has. A lot of people are fans of Blender because it's totally free, totally open source. I hate it. But you might not. You might look at it and see. Okay. That was word number 2, which is ascend. Do 2D stuff to practice, but graduate to 3D, graduate to 4D. All right, now we're going to get more controversial. Third word of advice as to what we should do is we should archive. We should archive the works that we make. What do I mean by that? What does that mean, like publish it on the archive? Not exactly, but kinda. When you put a preprint up on the archive, what are you doing? You are submitting it to them, you're following their standards, you get a timestamp on it, you get a thing that says you submitted this at this time. You can't undo it, you can't change it. If you do, it registers that you changed it on the state. All these things, you know this, right? Right. What you are doing when you are posting something on the archive is you are minting a token. Yes, you are all doing NFTs already. It's just that you're doing it on a centralized server that might go down. I don't know how many people know, but the archive was in quite a bit of trouble recently, both financially and in terms of leadership. It is not impossible to think that we might lose that very valuable resource someday. I have started taking some of my, what I really like to think of as best works, the things that I want to keep around for a while, and I have started minting them on blockchains, on things that are decentralized. There are two that I've played around with that I've found to be really good, useful, nice to work with. You may or may not have heard of these. The Ethereum blockchain is the most popular. It's got the best tools out there. It can be a little on the expensive side to mint, depending on how much monkey picture action there's going on at any given time. I find that recently, gas prices really low. The stuff that I've been minting recently, some of the videos that I just showed you from topological data analysis, $2.50, $3 to mint a JPEG like that. The vibe in the Ethereum world is sort of half monkey pictures for $1 million and half bankers. That may or may not be for you. There's a different chain that I've been experimenting with as well. This is the Tezos chain. This is very geeky. This is much more of an artist type community. Very inexpensive to mint on there. It cost me less than 15 cents to mint a token on the Tezos chain. The vibe is very much a Linux and LaTeX type of vibe. I think that if mathematicians, computer scientists get into this, Tezos might be where they wind up. Ethereum is going to be more popular, so maybe that. Don't know. I'm playing around with both under the artist name of Colimit, and there's a couple of different things that I'd like to say. First of all, is this weird? Yes. Okay, it's kind of weird. It's early, I think, but someone needs to come out and say, you know, academics, researchers, teachers ought to be using these tools. I'm going to do it. PowerPoint used to be weird. I started using PowerPoint more than 20 years ago in talks. People looked at me like I was from another planet. This was when we were still writing on transparencies. People thought this was weird, and it was kind of weird. If you would like to try it out, if you'd like to see what can you actually do with this stuff, other than try to sell it to people for millions of dollars, which is not going to happen with the works that we all produce. Take a look. I set up a couple of sample galleries on something called OnCyber. You could do it on your laptop. You could do it on your phone right now. You don't need any special equipment. You don't need to log in. You could just go there, bop in. It's a little virtual reality gallery that you could walk around, look at art. I'm playing around with how to design spaces in here. Eventually, it's going to be possible to just build your own little museum where you've got your stuff, where you can link to other people's museums in the same way that back when we were writing HTML web pages, you would link to another person's website. This is kind of cool. Okay. You may be skeptical, that's fine, but let me just mention a little bit of practical advice should you want to experiment with this. 1 year ago, I had never done any of this, wasn't interested in doing any of this. It's very recent for me. If you decide to play around on the Ethereum chain, I strongly recommend something called Manifold Studio. This is a setup that allows you to mint tokens, to set up collections. For those of you screenshotting this, I'm going to put all of this stuff on a Twitter thread sometime, I don't know, later this week. So it'll be out there. I'll put in details and links. What I like about Manifold Studios is it allows you to mint and own your own contract. It writes the solidity for you, but allows you to modify the contract, personalize it as you see fit, and then you own it. You mint through OpenSea, something else like that. You don't own the contract. You have to trust what they are doing. Very easy to use. Again, depending on gas prices, it can be relatively cheap. I like it a lot. If you decide to play around with the Tezos chain, which is much easier, less stressful to use, then I recommend using object.com. This allows you to just, once you've set up a wallet, just upload a file, put in some metadata associated with it, hit the mint button, and then you go. You can mint JPEGs, you can mint movies. With Object, you can even mint PDFs. Will there be a time when we're putting our preprints, our papers out this way? I kind of hope so. I think that would be kind of nice. A little bit of practical advice. Minting is kind of permanent, so don't put out things that you're going to be embarrassed of later. Yeah, I've never followed that advice, so whatever. Do be really careful with security, with privacy. Use a hardware wallet. And I recommend building an identity. I find that a .eth or .tez address is a useful thing. Won't take too long for you to learn how to get a Tezos domain or an Ethereum name. Okay, that's the 3 words. What was it? Produce, ascend, archive. Last word. Last word. The last word is weird. This whole talk. I told you it was going to be weird, did I not? Yes, I did. And we've gotten weird, but not weird enough. What do I mean by weird? I mean weird. But I mean weird in the sense that where this word comes from, the Old English that it's derived from, has a different meaning. It has a meaning of being connected to the spiritual, kind of, but really, technically, it has a divinatory component. When Shakespeare talks about Macbeth's weird sisters, they're weird not because they're creepy, they're weird because they can see the future. I mean all of those things wrapped up together. You should be more weird. You should allow yourself to do stuff that's a little strange. When I did all the chapter headings for elementary applied topology a long time ago, I was very weird in how I set it up. There were all sorts of literary and mythological images built into that in ways that I did not explain to people, and that's okay. That is weird, and I don't mind it. When I did the intro to my dynamical systems course, the videos all start off with this stuff. It's sort of meant to evoke like an old British mystery theater, something kind of a thing. The music is me, don't worry about it. What was up with that? What was that? Was that a crystal ball? What's that on the table? What are those things? Why are they arranged in that way? Is that a simplex? What is that? What's reflected in the TV screen? This is so weird. What does it have to do with T.S. Eliot's Wasteland? This is being a little bit weird in the sense of both future-oriented and connected to the spiritual. Dante was weird. Dante took all of the stodgy classical poetry of Virgil and just rocketed it into the future. He built, in his poetry, an entire cosmology for the universe, put Virgil in as a main character, and then put Dante in as the main character and wrote amazing poetry about it hundreds and hundreds of years ago, way, way ahead of his time. Who's the guy on the left? John Milton, that's correct. Paradise Lost, beautiful, beautiful English epic poem, similar to Virgil, very explicitly Virgilian, and what he called out. Who's the guy on the right? Anyone know? It's not the usual picture, but I wanted something that was facing forward. This is William Blake, who wrote so much weird stuff, including the epic poem called Milton, where he writes Milton in as a character of the story. And he writes himself in as a character of the story. Milton falls from heaven and enters Blake's ankle, just like Achilles, in this crazy story with a whole cosmology that he's built. Same kind of thing, inventing new ways of blending together artwork and poetry in order to touch the divine. That's really weird. I think weird is a good way to go, and that's the way that I want to end this talk. I want to thank you for your patience in what was a very strange talk, I know, and I would love to stop now, entertain questions, get your feedback. Thank you.
Can you? Okay. Thank you very much for this great talk. Do we have questions in the audience? You can, if you do, just stand up and I will put the microphone here on the stand. And you can ask your questions.
Hi.
Yeah, so that was for fun. Yeah. So it's not entirely for fun. The reflection is supposed to capture the idea that if you know enough about the local structure, you can see beyond the local. This is the whole idea of algebraic topology, is that if you know enough local structure and you assemble it together, you've got the global. The actual material shader that's used in those simplices, that was really interesting. I'm trying to capture higher dimensional simplices that, of course, you can't see. You can only see the outside. You can only see the two-dimensional faces. So I had a different shader for the two-dimensional faces that were isolated. But then for the three-dimensional and the higher dimensional faces, I was using different shaders that had a combination of some thin film stuff going on with some reflectivity channel in order to get at the idea that there's higher dimensions inside of there. I find it a real challenge to capture high-dimensional simplices in an animation. So the materials is what I was using to try to get at that. That was very observant. Yes, good question. The philosophy is that the figures were the exercises for the textbook. There were no traditional exercises. There are no exercises that you could assign in a course, although I have heard of one person who did assign a couple of problems in a topology textbook that said, explain this diagram, and then put in an image from my book. That's perfect. That's exactly what I'm going for. Yeah, that's a question that I think a lot of people who are experimenting with flipped courses have been dealing with. I've tried a couple of different ways of doing things. What I am currently using as my teaching model is to think about all of the video content as being like the textbook. So it's all up on YouTube. It is all sort of outside of class, where students are engaging with that on their time, on their schedule as they feel the need. And then what I will do is in class, I'll spend part of the time with a recap, a reprise of the material, just to reinforce it, to go over it. Of course, that doesn't have any of the animations or the illustrations, but if they've seen the videos, they're recalling it to mind. Or if they choose to watch the videos afterwards, then it fills in what they've already picked up base level. And then because the in-class lectures are sort of very truncated, much of the time that I spend with my students in class is much more interactive, much more problem solving, working through debugging things. I find this to be a good model, but I think a lot of people are experimenting with stuff. Again, I think about the video content as being a replacement for the text, not a replacement for the in-class instruction.
Thanks.
Do we have other questions? We have time for more.
Just a quick question. You mentioned Cinema 4D for your animations. And about your presentation, you also used Cinema 4D or your slides presentation?
So the slides are all PowerPoint. PowerPoint allows you to show videos, of course. So what I've got for much of the animated content that you're seeing here is videos produced in Cinema 4D, rendered out into MP4, and then just autoplayed in the PowerPoint. The way in which you can get PowerPoint to work with video for the production of video text, that's a whole different subject. I could and did teach a course on that. That's a big topic.
Thank you, thank you.
So I think it's a basic question. It's like you said, save the work on the blockchain, and I was wondering, like, because for the for the Bitcoin wallet, you have to synchronize all the whole Bitcoin network, kind of like all the nodes. Like when you save your work to the blockchain, do you need to synchronize like the whole net?
I'm really sorry, but being a little hard of hearing, I usually rely on looking at people's lips. If you could try that again without the mask.
So basically, it's like, do you need to synchronize the whole net with the blockchain when you save the work?
I'm still not sure that I understand the question. Do I need to synchronize what?
The whole nodes, like all the nodes in the blockchain.
Oh, in the blockchain, you're talking about the blockchain. That all happens autonomously. That's not anything that needs to be done. I'm very sorry for misunderstanding your question. I was in the mode of thinking about graphics, and a lot of the 3D software is node-based. That's what threw me. When it comes to minting something on a blockchain, you use the available resources, you hit the button, and it takes care of the rest. Yeah.
Okay, thank you.
Do we have more questions? I may have one question then.
Yeah.
Regarding the process, the creation process for this visual material, it seems that in all the examples that you showed, it was serving the purpose of teaching. And there you had the understanding of the concept prior to the creation of the visual content. My question would be, does it happen also for research, where you have a visual creation process, but you don't know in advance exactly what you want to express, or you produce some visual to yourself get a better understanding? Does it happen for you, or can you comment on that?
I think this is an excellent point, and something that I probably should have brought up and elaborated on more. The sort of mysterious process behind how you do research, for me as a mathematician, proving things, and then how you visualize what it is that you do. There have been so many times where I'm led to an idea, to a theorem, just by trying to draw a cartoon of what is happening. I think that with access to deeper visualization techniques, you can get at more. It's also easy to get more distracted with the, oh, I'm just going to tweak this and get the color scheme to look right. But absolutely, in a lot of the research that I've done, it's the process of trying to draw a simple cartoon that captures it that really unlocks what's going on mathematically. Thank you.
Yeah, so thanks for the talks. Just a small question. How many times the animation you showed us took for the rendering and all the stuff? I mean, is it interactive enough for dynamic interaction, or do you need a pre-processing which is too long for this kind of dynamic stuff?
Yeah, so I can't render things out like this real time. That's for sure. This is not like Unreal 5 or any of the game engines, which are just hyper optimized for that kind of stuff. But the fact that that does exist for games means that we get it eventually. So you might as well pretend that you're living in a world where you can do that eventually. At the moment, let's say those dynamical systems animations that you saw, each of those on a, not on a laptop, on a box, for me is, taking 20 minutes. Sometimes as much as an hour, sometimes as little as 5 minutes. But order of magnitude, a fraction of an hour. That is after having 5 years of experience playing with this stuff. In the beginning, I remember there's one video I made for topological data analysis type stuff, RIPS filtration, where I was just being an idiot with my materials, with my number of reflections, ray tracing options, things like that. And, it would take 24 hours to render. And I'd render it, and then, oh, this thing doesn't look quite right. I got to redo it. And then, boom, a week is gone. So there is a bit of a learning curve for it. But at present, the stuff I'm doing that's kind of in a cartoony style, it's not so ultra realistic, very reasonable render times. And that's a thing that only gets better and better over time.
Thanks.
All right. Well, I guess in the interest of time, we will move on. I guess we can thank the keynote speaker again for this great presentation.
Thank you so much.
Hello, my name is Aaron Nigmetov. Welcome to my talk, Fast Merge Tree Computation via SQL. This is joint work with Dmitry Morozov, way above, from Berkeley Lab. Merge trees have many applications. Our motivation comes from cosmological simulations, where we have the scalar field, the density of dark matter, and for different values of threshold t, we should find regions where this function is greater than t. Since the simulation runs on GPU nodes of a supercomputer, we should be able to compute merge trees on GPU. The algorithm that we chose is triplet merge trees. It is from TopoInVis 2017, proposed by Dmitry Morozov and Dmitry Smirnov. And the idea is that for each branch of a merge tree, you record the local minimum, b, where it started, you record the saddle, x, where it merged into a longer branch, and you record the information about the branch into which it merged, namely the minimum from which it started, bxa. So a triplet merge tree is a collection of triplets, USV, one triplet for each vertex u, and I don't have time to explain these definitions, but I can tell you that the algorithm works by processing all edges of a graph in parallel, and it doesn't use locks. It only needs atomic variables and compare and swap instructions. Since compare and swap is available both on CPU and GPU, it would be very interesting to see how it performs in GPU world. We use SQL. SQL is a standard inspired by OpenCL. It allows you to write your code in normal C++, and then SQL implementation will compile it targeting multiple backends, AMD ROCm, NVIDIA CUDA, OpenMP, whatever you need. How you express parallelism, you have the function parallel4. This function takes a lambda, and inside this lambda, you can process arrays using almost all standard C++ constructions. So HipSQL is one particular implementation of the SQL standard, which supports atomic variables and compare and swap. What you can do, you can take the last two vertices of each triplet, S and V. Let's assume that they are 32-bit integers, and you pack them together into a single 64-bit integer. Now your tree is an array, and you can easily express the triplet merge tree algorithm using SQL. We compare our implementation with the only other implementation that can run on OpenMP and GPU, parallel peak pruning algorithm by Carr and others from VTKM, and we find that on cosmological data, triplet merge trees perform much better than parallel peak pruning. There are also many other data sets where triplet merge trees are faster, but I must admit that this is input dependent, and there are data sets where Hello, my name is Aaron Nigmetov. Welcome to my talk, Fast.
Can you hear me? All right. All right, we had a little technical difficulty, but I think we got everything except the last two sentences. We're talking about the runtimes on the GPU. Do we have our speaker on? Yep, here we go. So I think we have some time for a few questions. While people get the questions ready and go to the microphone, I have a question. So in order to get the generalization of the code to be able to run on the GPU, you had to make some, changes to sort of how you store things that make it difficult to parallelize, right, on a distributed system. Do you have any idea how you would extend this to work in a distributed environment?
Hello. Sorry for this cutoff. The idea for the application that we're interested in for halo finding is that, in fact, we don't need most of the domain, so we can just first, given the threshold, identify and enumerate the vertices that we need and work only with them. And this indexing will have to be, it will be local on each MPI rank, and then we need some scheme that allows unique identification of each vertex. So actually, this is like work in progress. This is the next step.
Okay, great. Any questions for the audience? One more. I guess I have another question since we have some time. So the speed ups that you're getting, is there a particular type of data that this is sort of very well situated to get the speed up on versus where you won't get as much speed up?
Oh, that's a good question. We tried to analyze different statistics, but we still couldn't identify the single factor, because it could be 3D scans. There are 3D scans on which we perform better and on which VTKM performs better. So, okay. So far we don't have any good answer to that question. So.
Okay, great. We have a question.
I'm sorry, I don't hear anything.
Gunther Weber, Berkeley Lab. Arno, when comparing to PPPs, so did you compare to the full contour tree computation, or did you factor out the time for just the merge tree?
Just a merge tree. Oh, okay. So
Okay, all right. We're right on time, so let's thank the speaker. All right. So our next speaker will be Vitaly Kurlin. Did I get that right? Counterexamples expose gaps in the proof of time complexity for covered trees, introduced in 2006. All right.
Thank you very much. Very grateful to organizers for this live opportunity. This work is joint with my PhD student Yuri Yelkin, who couldn't come, so I'm replacing him now. What's the problem? The problem is k-nearest neighbor search. Well, the formal statement is on the slide, but hopefully you could guess what does it mean to find k nearest neighbors in a metric space. So let me highlight that this problem here is stated in and studied in our paper for any arbitrary metric space. And the key inputs here is a query subset of this metric space and a reference subset. So for a finite reference subset and any query point, we are looking for nearest neighbors of this query point within our reference subset. And in general, so for the first nearest neighbor, well, it's easy to imagine. We are looking for the shortest distance, but when we are looking for k nearest neighbors, we could have several identical neighbors at the same distance, and in that case, the problem asks to find simply k distinct point within, well, a certain range, so as formally defined here. So let me highlight, sorry about that, the naive algorithm to find k nearest neighbors is simply quadratic, so in the product, so it's simply proportional to the product of the sizes. So the real problem is to find them faster, ideally in a near linear time in the maximum size. And this problem turned out to be quite difficult. So the theoretical attempt to justify a faster algorithm appeared in ICML 2006, and it was called a cover tree. So this is a data structure specifically designed to justify a faster near linear time search. So the formal definition of this cover tree is rather complicated, and this ICML paper is rather shortened. Even in the extended version, it wasn't clearly defined, but we have tried our best, and this is a formal definition. So a cover tree basically is based on the filtration of subsets. So Ci starting at a level so-called plus infinity, the root node, and then these subsets are growing and finally capturing the whole reference set. So the covering condition means that for every point P, we can find another point Q within a certain distance bound. So these distance bounds here vary as 2 to the power I, so where I is our index of these filtration subsets. And the separation condition means that the points are not very close to each other in this subset, so they're well separated. So what was the problem in these past proofs? So essentially, the proofs were simply too short, not enough details to cover, and the key gap was that the number of iterations was wrongly estimated in terms of a maximal length of a road to node path. And the tree on the left basically shows an example where it doesn't work, where we need simply to visit many branches in this cover tree, so deep enough, and that's how we essentially get a quadratic number of iterations necessary for this particular data set. So these gaps were fixed now by a new structure called new compressed cover tree. So this picture illustrates the difference between, so on the left, the implicit cover tree, the explicit cover tree, which is a bit simpler as you see, but it still contains infinitely many repetitions of every nodes, and the finally compressed cover tree on the right-hand side, which is really much smaller, so containing only 5 nodes with only relevant connections. So this table summarizes actually the next results about the time for constructing these data structures, and in the last line, the compressed cover tree. This table summarizes the time complexity results for nearest neighbor search after a data structure is already constructed. And finally, in the final slide, let me mention that this asymptotic complexity, this finally proved asymptotic complexity, was practically used to justify a much more important result in a very different work, which will appear in NeurIPS, when we considered periodic crystals up to isometry, and we studied them purely geometrically and extended with, well, we call it visual hint from Richard Feynman, who compared here in this very simple table on the left, simply cubical crystals with different chemistry, but they also differ geometrically. So we have extended this comparison to all real known materials by invariants that are based on nearest neighbors. So that's why this algorithm was important. And the main conclusion is that we now have a space. So maybe Richard Feynman was dreaming exactly about that space at the bottom, but now it's called the crystal isometry space of all isometry classes of periodic point sets, where real materials can be seen as stars. So, and a complete isometry invariants now serve as coordinates in this space. Thank you.
All right, great work. I think we have time for a quick question. All right, I have one. So the counterexamples you gave are sort of very nicely drawn out and really easy to follow. But I was wondering if you had any intuition of what kind of data would produce the situations that would break the assumptions from the previous work.
If you could get a slide back,
okay.
Then yeah, there was actually a graph showing this data. So if the slides can be returned.
Can we get the slide back for a second?
Thank you. So let me, so this graph on the right-hand side, so that it's not ideally visible, but if you, so these points are simply used in this counterexample. So we have a very simple data structure here. 2 points connected by several edges, and we in addition take these middle points. So of course we specify distances, so they are a bit non-trivial here, so powers of 2. But the example itself is not really complicated, so it is simply on the same slide. Thank you.
All right, let's thank our speaker. All right. Speakers, I guess we thank both speakers since we're at the end of the session. So we're in a break right now. We're going to be back in this room at 3:45, and see you there.